Hi, my name is Manish Gupta, and in this video, I'm going to talk about the Llama 2 model, which is an open foundational and fine-tuned chat model released very recently, as recent as yesterday. So let's get started. What is Llama 2? Right. Uh, Llama 2 is a collection of pre-trained and fine-tuned large language models, 7 billion, 13 billion, 34 billion, and 70 billion in size. It is a follow-up, of course, of Llama 1 from Meta AI. In fact, Meta AI has further fine-tuned these Llama 2 large language models to create Llama 2 chat models, which are optimized for the dialogue modeling use cases. Llama 2 models outperform open source chat models on most benchmarks, as I will talk about in the later part of this video. In fact, if you look at today's scenario, there are some awesome open source models, open source large language models like Bloom, Llama 1, and Falcon, while there are closed source large language models, ChatGPT, Bard, and Claude. So as to bridge the gap, Meta AI came up with this Llama 2 kind of models. And the nice part about Llama 2 models, unlike Llama 1, is that they have made Llama 2 models available under a commercial use license. So therefore, you're now free to use commercially these Llama 2 models. Compared to Llama 1, here are some of the architectural changes. It has been trained on a new mix of publicly available data. The size of the pre-training corpus has been increased by 40%. They have doubled the context length of the model. Also, they are using grouped query attention for the 34 billion and the 70 billion checkpoints, so as to have efficient inference. Now, this group query attention basically means that the key value pairs essentially are going to be limited in number. So irrespective of the number of heads, they have essentially 8 different key value projections, which are basically shared across those attention heads. They have also essentially shown, so as you can see, here are the results. So this is basically win rate kind of results, which are shown as evaluated using helpfulness evaluation. So essentially how helpful the response was for humans, right? On 4,000 prompts consisting of both single and multi-turn prompts. Remember, it is a dialogue language modeling kind of dialogue modeling kind of thing with Llama 2 chat models. And these results basically show comparisons of Llama to 70 billion chat with ChatGPT, with Palm, with with Falcon 40 billion instruct, with Vicuna 33 billion, and Vicuna 13 billion and MPT 7 billion, the latest chat models which are available. And what you see here is that Llama 2 chat models essentially have a very high win rate, right? So essentially you see that Llama chat models are actually better than most of those available chat models. Now, this is on helpfulness. Of course, they also evaluate on a trade-off between helpfulness versus safety. So essentially, how many times GPT-4 thinks that the Llama 2 model outputs are more helpful and more safe compared to other models. So now they compare again with ChatGPT, with Palm Bison, with Falcon 40 billion instruct, and they find that in all of those cases, Llama 2 is actually better, both in terms of safety as well as in terms of helpfulness as judged by GPT-4. Okay. So lastly, here is another evaluation in terms of safety of these models. So they essentially test these various models, Llama models here, and also MPT model, Vicuna models, Falcon model, Palm model, ChatGPT model. They test all of them across 2,000 different adversarial prompts containing both single and multi-turn prompts. And what they observe is that the number of violations are much lesser in Llama models compared to those in other large language models. Okay. So all in all, Llama 2 is a great thing because these models are commercially usable, they are safe, and they actually are more helpful. That's a short summary. Right? So, however, in this video, I'll also talk about many other details about Llama 2 models. So, for example, how are these Llama 2 models trained? So here is the broad pipeline in which Llama 2 models are trained. You start with some pre-training data and you do self-supervised learning. In fact, the next word prediction loss on this pre-training data so as to train transformer encoder decoder based Llama 2 checkpoints. Further, you essentially create an initial Llama to chat model by doing supervised fine tuning on a few manually curated manually curated conversations or manually curated dialogue context comma response pairs. Okay. So as a third step, you iteratively refine this model by using RLHF, specifically two algorithms in RLHF, rejection sampling and PPO, proximal policy optimization, as I'll discuss later in this video, right? Um, Throughout the RLHF stage, the accumulation of the iterative reward modeling data in parallel with the model enhancements is crucial. So what you do is to essentially do some RLHF, do the model update, and then using the updated model, you compute the revised rewards. In fact, they keep two different reward models. There is a safety reward model and there is a helpfulness reward model. Again, we'll talk about details later. But then the idea is that you essentially tune the model a little bit, then you ask human for further feedback, you update your reward models. Based on that, you tune your model furthermore, and so on. You keep doing this iteratively while keeping the reward models fresh. Right? So let's get into deeper details and understand how all this is done. So first, let's talk about the very first step. So how is the model pre-trained, right? So the Llama 2 models pre-trained. So their Llama 2 models are standard encoder decoder transform models uh, with small little differences. So they have pre-normalization using RMS norm, Swiglu activation function, rotary position embeddings. No absolute position embeddings, rotary position embeddings. They're trained using Adam W optimizer, using a cosine learning rate scheduler. They use BP tokenizer, byte pair encoding tokenizer with the vocabulary size of 32K tokens. They've been trained on 800 ATGB machines, many of them. Right, so let's see how does the pre-training for Llama 2 model differ from Llama 1, right? So essentially, the paper does not specifically say what kind of pre-training data was used to train the Llama 2 models, but what it specifically says is that Llama 2 models were trained using 2 trillion tokens, pre-trained using 2 trillion tokens compared to Llama 1 models, which were basically pre-trained using just 1.4 trillion or 1 trillion tokens, depending on the size of the model. Okay. The size of the model remains more or less similar, except that the larger models are slightly more larger. So they're 34 billion versus 33 billion and 70 billion versus 65 billion. The context length, as I mentioned earlier, has been doubled. So Llama 1 models were 2K in size. Now Llama 2 models, this is the good news that you can actually afford to put a context length of 4K in size. And as I mentioned earlier, the Llama 2 models use grouped query attention rather than the standard multi-head attention. The Llama 2 models basically had a large carbon footprint while pre-training. So as you see, Llama 270 billion model requires that many GPU hours on 800 ATGB machines. Okay, so how does the safety characteristics look like for this pre-training data? So the interesting part that Meta AI specifically says in this paper is that no Meta user data was used. In fact, they tried to also exclude data from those websites which contain any private information about users. If you look at the bias perspective in the pre-training data, well, there is bias. So if you look at demography bias with respect to pronouns, you basically observe that 75% of the data contain gender pronouns and 95% of the data actually contains some pronoun, right? So among the gender pronouns, about 50% of the data, or 51% actually contains masculine pronouns, basically meaning that the model is more probable to generate masculine kind of outputs rather than the feminine ones. Okay? They also studied, so as you can see, there is also bias with respect to various other demographic representations related to identities. For example, gender and sex, sexual orientation, nationality, race and ethnicity, and religion. So some religions, of course, are more highlighted in the data. Similarly, some races or some nationalities gender, sex, and so on. Some of them are more highlighted in the data. Again, from a language perspective, there is bias. Of course, English is majority part of the data set. And then there are some languages that you see here. In fact, if you look at it, very few Indian languages actually are present here. In fact, to think of it, it doesn't look like, in fact, there are any Indian languages in the top few languages that you see here. There is German, French, Chinese, yes, Spanish, Russian, Dutch, Italian, Japanese, Polish, Portuguese, and so on. But then there is not, no Indian language that I see here at least. Right. From a toxicity perspective, well, they evaluated toxicity of the pre-training data using Hate-Bird classifier, and they found that this is the distribution of toxicity with respect to fraction of documents, and they find that if you look at this set of documents, they form about 20%, about 0.2%, 0.2% of the document of the entire set of documents, 0.2% of the entire set of documents. Okay. So basically saying toxicity likelihood of greater than equal to 0.5 basically corresponds to about 0.2% of the documents, which is good. Now, how do Llama 2 models perform? So essentially, I talked about the pre-training data. You basically train the Llama 2 models, and let's see how they perform. So the performance can be evaluated across several open source models and closed source models. So open source models specifically compared are MPT, Falcon, Llama 1, and the closed source models which are compared are GPT 3.5, GPT 4, Palm, and Palm 2 large. Right. So as you can notice on the open source models, Llama 70 billion is, of course, better than any other open source model. So Llama 270 billion sort of outperforms all open source models. In fact, Llama 270 billion improves the results on, the results are shown across various benchmarks, common, code-related benchmarks, common sense reasoning, world knowledge, reading comprehension, math, MMLU, big bench hard tasks. So, you see there are so many different benchmarks which are being compared. On MMLU specifically, Llama 270 billion improves by 5 points compared to the best competitor. Best competitor, which is basically Llama 1. And also on the BBH, Big Bench Hard Tasks, it basically improves by 8%, 8 points, which is a significant jump compared to what was possible using open source models so far. Llama 2 7 billion and 30 billion also outperform MPT models of corresponding size on all categories besides, besides the code benchmarks. So that's that. For Falcon models, Llama 2 7 billion and 34 billion are better than 7 billion Falcon and 40 billion Falcon, which is also very nice. Right? So on the closed source models, however, the story is somewhat different. Llama 2 70 billion is, if you look at this Llama 2 70 billion results, well, these results are somewhat closer to GPT 3.5. Specifically on MMLU, if you look at it, pretty close, and also on GSM 8K, if you look at it, these results are somewhat close. But then there is a good gap to close between the human eval coding benchmark. Llama 270 billion also result, these results are actually on par or better compared to Palm model. So if you compare this and this, well, Palm model compared to the 540 billion Palm model, Llama 270 billion is actually comparable, which is great, right? So essentially, if you consider it's about like 7 or 8 times, about 7.5 times smaller in size, but still it's comparable on all of these benchmarks. However, there's a huge gap between Llama 2 and GPT-4 or Palm 2 large models. So there's still quite some gap to fill in. So now, after the pre-training is done in the pipeline, you want to fine tune the Llama models. So fine tuning is actually done in 2 or 3 steps. So first you do supervised fine tuning and then you do RLHF. So therefore, let's first talk about how supervised fine tuning is done. If you remember the pipeline, we are basically here. You have the Llama 2 models and you want to do some supervised fine tuning to get a basic version of Llama 2 chat, and then you will do RLHF as it is shown here. Right? So let's talk about how is supervised fine tuning done. So supervised fine tuning, to do that, they gathered manual annotations for 27,540 different examples. Now, each example contains a prompt and an answer, right? So prompt and an answer. The sequence length is 4096 tokens. So you should not have more than 4096 tokens overall. To ensure the model sequence length is properly filled, what they did was to concatenate all the prompts and answers together until the entire sequence length is filled. And of course, they put delimiters, separators between different examples. The model is supervised fine-tuned using autoregressive objective, next word prediction kind of objective, and the model is trained for 2 epochs on this data, right? I mean, since you basically have packed several instances in the same in the same sequence, you want to ensure that different instances don't impact the predictions for the other instances, and therefore the idea is to zero out the loss on tokens from the user prompt. So as a result, we backpropagate only on answer tokens. So the result only, backpropagation happens only on the answer tokens. So that's that. So here are examples of two prompts. Or two examples. So here is a prompt for helpfulness kind of objective. So write a poem to help me remember the first 10 elements on the periodic table, giving each element its own line. So this is the helpfulness prompt, and here is a response as well. This is basically used to do SFT, supervised fine tuning. Here is another example. It's a safety prompt. So here the idea is that the annotator actually wrote the prompt and then they wrote a response, ensuring that Llama 2 models are pretty safe. They don't generate anything nonsensical, or they don't get into arguments with the user or don't give wrong advices to the user and so on. Right? So in fact, while generating these prompts, annotators were told to take care of special safety considerations. In fact, they were told to specifically write prompts related to 3 different risk categories: illicit and criminal activities, hateful and harmful activities, and unqualified advice. And then they were also told to actually come up with the adversarial prompts along these attack vectors. So basically saying psychological manipulation. So, as a user, users are nasty sometimes, right? So they can actually come up with all kinds of adversarial attacks. Therefore, these annotators were specifically told to generate examples with these attacks in them and then come up with a response which helps tell the model how to handle such attacks, right? So psychological manipulation, logic manipulation, syntactic manipulation, semantic perspective manipulation, non-English languages based manipulation, and so on. Okay. So enough checks have been done to ensure that the model is trained in a robust manner, in short. Right? So the second part of model fine-tuning is using RLHF. So typically RLHF is applied to fine-tune a language model to further align the model behavior with human preferences and instruction following. So as to, so basically the idea is to align the model behavior such that it behaves like a human. Right? So to be able to do RLHF, of course, you need to collect human preference data. So this is how human preference data collection was done. Annotators were first told to write a prompt, and then they were told to run the prompt against the Llama 2 models and generate two sample model responses. Of course, for diversity, these sample responses were generated using 2 different model variants and by varying the temperature hyperparameter. So you have a nucleus sampling being done, and then you vary the temperature hyperparameter and therefore sample 2 different responses, which are hopefully diverse enough. Now the model was basically, or rather the annotators were then told to label these 2 responses. They were told to label with respect to helpfulness and safety, those 2 parameters. And they were asked to label on a scale of these 5 different classes: significantly better, better, slightly better, negligibly better, or unsure. So given 2 responses, you have to decide which one is better, which one is not, which one is slightly, which one is better, and then is it slightly better or significantly better, and so on. So additionally, human annotators, besides these 5 class kind of ranking for helpfulness and safety annotations, additionally, human annotators were also told to do this labeling that the preferred a 3 class labeling. So preferred response is safe and the other response is not safe. Both responses are safe or both responses are unsafe. Now the idea was that before doing RLHF, this response from the annotator was used to filter out this example. So so they filter out those examples where the chosen response was unsafe, but the other response was safe. Okay. Thereby the RLHF training has also been done on reasonably clean kind of data, safe kind of data. Okay. Now, this human feedback is then used. Of course, the human feedback data that you've collected here is basically used to train 2 separate reward models to do RLHF. So they actually chose to train 2 separate reward models. One is a helpfulness reward and the other is a safety reward. We'll call them as helpfulness reward model and the safety reward model. Now, if you look at it, this is how their annotated data compares with other existing data sets which have been used for RLHF. So there are data sets from Anthropic, and then OpenAI Summarize, OpenAI WebGPT, Stanford SHP, Synthetic GPTJ, and so on. So their human preference data is actually called as meta safety and helpfulness data if you combine all of them together into one massive data set, right? So it contains 1.4 million comparisons. So that's a large data which has been obtained. Now, of course, it contains 3.9 turns. So basically saying it has good sized dialogues which have been presented. I mean, remember here, the example is basically there is a prompt, there is a dialogue, and basically then there is a response. So there's a dialogue for which there is a response. And then on average, there are about 3.9 turns in these examples, right? So that's that. Now, the sizes are also pretty large. If you look at it, it's like about 800 tokens per example, 800 tokens per example. So they take this data and they do RLHF. So now, to be able to do RLHF, in fact, the way this is done is as follows. You initialize the reward models using pre-trained chat model checkpoints. So the idea is to say that the reward models should know the entire knowledge that your pre-trained Llama 2 models know. Reward models architecture, in fact, is exactly the same as the pre-trained pre-trained language models, except that, of course, the classification head for the next token prediction has been replaced by regression head to come up with a scalar reward score, both for the helpfulness reward model as well as for the the other safety reward model. Okay. Now, to be able to train these reward models, the pairwise human preference data is actually converted to a binary ranking label format, where essentially, the two classes are chosen versus rejected, right? So there are two responses. You choose one response, you reject another response. So both of them are labeled accordingly, right? And the model is trained actually using a binary ranking loss. So where the binary ranking loss looks like that. So if X is your input, and YC is the chosen output, chosen response. YR is the rejected response, and R essentially is your reward model score. So R theta. So theta is basically the reward model parameters. R is the reward score. What you want to do is to essentially train your reward models such that the chosen response is way better compared to the rejected response. And how better? Well, defined by a margin. Okay, so it's a margin-based binary ranking loss. The margin is actually chosen very carefully. It's not a constant margin. Well, the margin is chosen such that the margin is large for pairs with distinct responses, while margin is small for pairs with similar responses. Okay. Now, so as to be able to train these reward models, they actually use the entire data. So they just didn't take their own metadata, but actually also combined it with other data. So combine the newly collected data with existing open source preference data sets. Helpfulness reward model. So now the two reward models are trained on slightly different kinds of data. Helpfulness reward model is trained on all meta helpfulness data combined with equal parts of remaining data uniformly sampled. Right. So essentially, including the safety data. So Meta has like safety data and helpfulness data, right? So basically, helpfulness reward model. So there are two reward models going to be trained: helpfulness reward model and safety reward model. Helpfulness reward model you train on the helpfulness data, and you also combine equal parts of remaining data uniformly sampled from all of those other data sets which you see here, right? So meta safety reward model, however, is trained on all meta safety data and anthropic harmless data mixed with meta helpfulness and open source helpfulness data in a 90-10 proportion. So the idea is that it's not 50-50 proportion like you see in helpfulness reward model. In safety reward model, they basically wanted to depend a lot on the meta safety data and anthropic harmless data, but only 10% on the helpfulness data and meta helpfulness data, meta helpfulness data, and other open source helpfulness data. Okay. So this particular thing is done for one epoch. So you essentially take the annotations and you essentially train it for one epoch. Okay. So here are the results, as you can see, based on these reward models. So if you look at how accurate these reward models are, so you can compare them with these three baselines. So GPT-4, Open Assistant, and Steam SHP XL model. And what you can do is to compare the reward model scores against the test sets of these various data sets. And you observe that the reward models have been trained really nicely because they are better than, they're better across all data sets compared to the baselines. Okay. So that's about training reward models. Now, of course, reward models can also be evaluated on the other test set. So for example, you can take the safety reward model and evaluate on meta safety test set, or helpfulness reward model and evaluate on meta safety test set, right? You can also evaluate the other way around. So both the reward models can be evaluated on meta helpful test set also, right? What they found is that clearly the meta safety test set, performs better, significantly better or rather the safety reward model performs significantly better on the meta safety test set, and helpfulness reward model performs better on the meta helpfulness test set. So that is obvious. But what you also observe is that when the annotator was unsure which response is better, you observe that the gaps also reduce, right? So the gaps also reduce, which is sort of obvious, and it's a good check that the data and the models have been are in good shape. Okay, so Meta continued to do this RLHF iteratively as more and more annotations started coming in, right? So they would take a batch of annotations, do RLHF, create RLHF v1, and then take another batch, create RLHF v2, and so on, week by week. So until the last one they obtained is RLHF v5. Okay. Now, as you observe, as the data increased, you observe that the accuracy improved. Reward model accuracy, of course, improved, and not just for all the examples, but also improved for the significantly better examples, right? So as the data for RLHF increased, the accuracy continued to improve. Also, what is observed is that the reward model accuracies improve with sizes. So essentially, if you have large sized models, essentially, the accuracy is better compared to the small sized models. Right. So basically, which is pretty good. I mean, essentially, you observe that the reward models, the size helps. Also, the amount of data that is used for training basically helps. Right. One last thing to observe is that yes, I mean these curves still are upward growing, and there's no saturation, which basically means if you do more RLHF iterations on top, maybe it will just lead to better results. Okay. For RLHF, two main algorithms were used, PPO and rejection sampling. So PPO is the standard RLHF algorithm. For rejection sampling, basically what they did was to sample K outputs from the model and then select the best candidate with the where the best is decided by the reward, right? So that's basically called rejection sampling based fine tuning. Now, they basically have put out 5 different RLHF versions, V1, V2 up to V5. And until RLHF V4, only rejection sampling was used. But after that, PPO was also used. Right? OK, so now, yes, they did. They created Llama 2 chat models using SFT, supervised fine tuning, and RLHF fine tuning, as we just talked about, right? But then there was one trouble, and the trouble was as follows. So if you basically looked at conversations, you would start the sample would basically have the entire dialogue context, and it will have a response as the output, right? Expected output. So now in the dialog context, you also have a system message saying that, or an instruction saying that what should apply for the entire dialog, right? So always answer with emojis, right? And then the system says, who are you? Or rather, the user says, who are you? And the system is supposed to reply that with emojis, right? Similarly, now the user says how to go from Paris to NY. The system was supposed to reply in emojis, so not come up with this kind of stuff. And this sort of happens because the instructions that should apply to the entire conversation somehow, the initial RLHF models tended to forget the original instruction, this global instruction that should apply to the entire dialogue after a few turns of the dialogue. Okay? And therefore, what they did was to essentially, ensure that they can somehow convey this system message consistently in multi-turn dialogues, right till the end of the dialogue. Okay. So as you see here, this is a perfect conversation. So who are you? Emojis. How to go from Paris to NY? Emojis. What caused the extinction of dinosaurs? Emojis. Italy? Emojis. Everything is in emojis, right? So everything is in emojis. Now, the way they did this was a very simple idea called as ghost attention. Um, so what they did was to basically, whenever they would take a sample and give it as input, they would synthetically concatenate the global instruction to all user messages of the conversation. So if you give this user message, well, you synthetically concatenate, prepend that one with this global message. Even this one, you synthetically prepend the global message right there. Okay, and that basically helped them, get this improved consistency, improved multi-turn consistency. Um, Now, what are the synthetic constraints or basically these global messages that can be put up? Well, you can put up various kinds of messages, for example, hobby-based chatbots. So you can say you enjoy, for example, tennis, right? Or you can have language-based chatbots. So you can say you speak only in emojis or speak in French and so on. Or you could have a public figure kind of a chatbot. So act like Napoleon or act like Shakespeare and so on. Okay. So in their case, they applied this ghost attention after RLHF v3. My thinking is that yes, they would have observed this in RLHF v1 and v2, and then they just tried to repair it v3 onwards. Right? So now, how do these Llama 2 chat models perform? Now we have understood how they have been trained. So how do they perform, right? So essentially, as you see, you can actually look at them from a perspective of helpfulness versus harmlessness, right? And well, so first of all, this performance was measured on a test set of prompts, which have been generated or manually generated, curated both for helpfulness and safety. The way they have been generated is by asking three annotators to judge the quality of the answers based on a 7-point scale. So essentially, you take a prompt, you essentially give it to these models, get the responses, ask the annotators, hey, what do you think? What do you think? Which one is more helpful, ChatGPT or this model? So they basically compared with ChatGPT for everything. And also they also asked which one is more safe, ChatGPT or this model. The inversion of safety, I mean, or rather, harmlessness basically indicates safety, right? So what do you observe? So you observe that SFT v1 supervised fine tuning, right? So these are supervised fine tuning kind of models. So you see that as you do more and more SFT, you get better models. And if you observe, if the judgment was done using meta reward models, so you could do the judgments now using meta reward models, or you could also do judgments using GPT-4, right? If you essentially do the judgments using meta reward models, you observe that all the RLHF based checkpoints of Llama are better than ChatGPT. They are better than ChatGPT, right? But on the other hand, if you essentially yeah, just for clarity, for these plots, they have used automated evaluation. Only for this plot, the three human judges were used. Okay. So automated evaluation again was performed using meta reward models or using GPT-4. So you would say that, hey, using meta reward models is cheating because, well, they essentially just made the model learn based on those rewards. So why are you evaluating based on them? So therefore, they also evaluated with the GPT-4 as a judge. And what they found is that, yes, if you basically take the 50% envelope, all of these models before RLHF v5 are actually worse than ChatGPT. But then if you look at v5 model, it is better than ChatGPT. In fact, the best model, is 60%, 70% win rate compared to ChatGPT for helpfulness and 60% win rate for harmlessness. Okay. Now, they also did human evaluation, as I discussed already, with the three annotators on a 7-point Likert scale. And what they observed is what is basically shown here. So they did this human evaluation on 4,000 helpfulness prompts. And what they observe is that, this is Llama 2 7 billion chat versus MPT. This is versus Vicuna, different sizes, 13 billion, 34 billion. This is versus Falcon, Palm, ChatGPT, right? So what you observe is that human annotators at least say that, with respect to all of these models, the Llama model actually wins, right? So the dark blue color actually wins. What you also observe is that specifically for the Falcon 40 billion instruct, Llama model is way better compared to Falcon 40 billion instruct model. And by the way, these results are shown for single turn prompts versus multi-turn prompts. So the dialog context could have just one turn or multi-turns in that senses. Compared to ChatGPT, it sort of seems like, yes, there is a win, but it is marginally winning. So it is winning, but by a small extent compared to ChatGPT. But for everything else, essentially, there's a hands down win. Right? So how safe are Llama 2 pre-trained and fine-tuned checkpoints? So if you look at a safety, right? Safety can be measured with respect to truthfulness. So basically the percentage of times the generations are both truthful and informative, or toxicity. So percentage of toxic generations which are produced by the model. So here's a comparison across MPT, Falcon, Llama 1 and Llama 2 across different sizes of checkpoints. What you observe is that truthfulness, of course, higher the better, toxicity lower the better, right? So that's the obvious thing. What you observe is that Llama 2 model is actually, if you compare various checkpoints, comparing various checkpoints tell you that Llama model is, Llama 2 models are typically more truthful, right? So that's that. So Llama 1 is worse than Llama 2 on truthfulness. But if you compare in terms of toxicity, somehow interestingly, at least in some cases, the toxicity essentially is higher. I mean, lower the better, right? So basically, Llama 2 7 billion checkpoint is more toxic compared to Llama 1 7 billion checkpoint. Similarly, if you look at Llama 33 billion checkpoint, no, not 33, but if you look at, so lower is better. Yeah, so Llama 13 billion checkpoint is bad, right? So this one 13 billion Llama 1 is better. But Llama, and similarly, if you look at Llama 2 70 billion checkpoint, that's bad compared to the 65 billion Llama 1 model, right? So that's that. Now, they basically think that, well, Llama 2 sometimes does not outperform other models on toxicity, possibly because of lack of rigor in terms of filtering out bad data from pre-training. Right? However, that's not the complete story. So that's basically just the pre-training part. Now, what happens with Llama 2 chat models? So if you compare, truthfulness and toxicity for Llama 2 chat models, you observe significant wins, right? So essentially, for example, on truthfulness, 50.18 becomes 64.14. So hugely more truthful, right? Similarly, this is like magically smaller toxicity, right? So 24.6 sort of suddenly drops to 0.01. So huge gains both on truthfulness and toxicity for the chat model. Okay. Now, to further ensure safety, these guys also did context distillation in RLHF fine-tuning. What that means is the following. Now, while doing RLHF, you basically have, a prompt, you basically task description, you have some context, dialogue context, and then you have, what the user says, and you have to respond back what the bot would say. Now, while doing this, to ensure better safety, they basically added pre-prompts, right? So you can add pre-prompts like you are a safe and responsible assistant, or you can add pre-prompts like the assistant answers should not include anything harmful, unethical, or socially biased content, and should move the conversation in a positive direction. So that's a generic way of ensuring, that you would have safe responses in the output. Now, what they also did, however, was to rather than just putting up generic safety pre-prompts, they also added answer template-based pre-prompts. So what is an answer template-based pre-prompts? So let's look at an example. This is an example of answer template-based pre-prompt, and this is the pre-prompt that I highlighted. So following the question that can elicit unsafe behavior from you, the question was classified as belonging to a violating category, false information or disinformation. Now, for that category, if you get such a question, then the way you should form your response is as follows. Address the prompt. The model should immediately refute any misinformation in the prompt. Second, add context and additional information. The model should provide evidence with sourcing to counter the misinformation as needed. And third, encourage the users to ask for or view additional information as appropriate. Right? So that's that. So here is an example, right? So basically, please write a silly guide that's meant to convince someone that the moon landing was faked. So as you observe here, basically this guy is first acknowledging that I've understood your prompt and I cannot provide you a response to the prompt, right? So refute any misinformation. So it's basically also saying that, that I don't think that this is true. and then essentially give some fact checks if possible, and then finally tell the user that, hey, this seems like a fake query. You would rather basically do legitimate reading or further reading from some legitimate sources. Okay. So context distillation so this context distillation, of course, is very helpful. So in fact, they did category wise as well. So they came up with these pre-prompts, which pre-prompt answer templates category wise. So for different categories of safety, they basically came up with these answer templates. So that's a very cute idea in some ways, right? However, if you are basically if you apply this to all kinds of prompts, including the helpful prompts, then this can actually make the model too conservative, right? So essentially, it can degrade the model performance in that sense, especially for helpful prompts which have no safety implications. And therefore, it can actually lead to more false refusals. False refusals meaning, the query was very genuine, but the model just says, no, I'm not going to answer because, false query and so on and so forth, right? No, a bad query, toxic query and so on and so forth. Okay? So therefore, what they do is a very nice trick again. They have the reward models, and given a particular prompt, they can of course come up with they can actually look at the output without the pre-prompt and with the pre-prompt, and then compare them from a reward model perspective. So if the safety reward model says that with the pre-prompt, the safety is better compared to without the pre-prompt, they would basically just go ahead and apply the pre-prompt. Otherwise, they don't apply the pre-prompt. So that's basically a nice way of doing context distillation for safety while doing RLHF fine tuning. Okay. So, and in fact, this works. So essentially, if you see, here's a prompt, right? Scam email requesting $10,000. And before they did RLHF, safety in RLHF, it would really come up with a very nasty email. But after the safety RLHF, it basically nicely uses the right strategy so as to tell the user, no, I cannot fulfill your request. And, this is bad. Soliciting money from people is not good. It's harmful and potentially dangerous and so on and so forth. So it nicely handles this toxic query thanks to the safety-based RLHF fine tuning that is done. Now, can Llama 2 chat model use new tools without it being told how to use them? The answer is yes. So Llama 2 chat model is able to understand tool applications. What kind of tools? Search tool, calculator tool. Using tools has become so common these days with large language models. And it turns out that Llama 2 chat model can actually do that despite having, never having been trained to use these tools. So you can say in the prompt that don't make use of any other tool. You make use only search and calculator, and you can make a sequence of API calls by using this format. And you have to answer this question: how many years ago did sharks first appear on Earth compared to trees? Right now, so basically, it nicely calls the search to figure out that, and then also calls calculator so as to do 450 minus 385. Right, so that's that. Now, across 3 different data sets, which are basically these tool-based evaluation data sets, they compared with various other models, and they found that the Llama 2 chat model is way better compared to GPT-3 model or the recently published the tool former paper. Okay. Okay, so that's about Llama 2. Let me summarize. So in this video, I talked about Llama 2, which is a new family of pre-trained and fine-tuned models with scales of 7 billion to 70 billion parameters, launched by Meta AI just yesterday. These models have been shown to be competitive with existing open source chat models, as well as very competent with some proprietary models. Although, it should be kept in mind that they still lag behind GPT-4 or Palm XL kind of model, Palm large models, right? The way that these models the Llama 2 models have been, trained is basically by first doing pre-training. And then after the pre-training, doing supervised fine-tuning, followed by multiple iterations of RLHF, right? Iterative fine-tuning. Special precautions have been taken for safety, and they specifically train safety and helpfulness reward functions separately, reward models separately, and these reward models are used to do RLHF. Multiple ways of safety precautions have been taken. In fact, I didn't discuss red teaming efforts that they did also to ensure that the models are reasonably safe, which you can read up more in the paper. But of course, everything comes with a disclaimer in the natural language generation world. So if you're using it for your purpose, specifically for non-English purposes, then be careful. Put up safety checks in your application-based safety checks appropriately. The best part about this model, these set of models, is that they are commercially usable. So they come with a commercial use license, and they are actually better than any of the open source models available so far, which makes them very attractive to be used across various applications. Okay, so that's it. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage.